Hello student, and welcome to the course Urban Rail Transit Tracks, Stations and Yards. In this lesson, we'll dive into the number and angle of turnout common crossings. Understanding these elements is essential, as they are the building blocks of the efficient urban rail network design and operation. A common crossing is designated either by the angle the gauge faces make with each other, or more commonly by the number of the crossing, represented by n. There are three methods of measuring the number of crossing, and the value of n also depends upon the method adopted. First, let's discuss the centerline method. This method is used in Britain and the USA. In the method, n is measured along the center line of the crossing. You can use the following formula to get n. The alpha refers to the angle of the crossing. Then the cotangent of alpha over 2 equals n divided by 1/2. After transformation, the n goes to 1/2 times the cotangent of alpha over 2. The right angle method is used on China and India railways. In this method, n is measured along the base of the right angle triangle. This method is also called Cone's method. In the right angle method, n is the cotangent of the angle formed by two gauged faces. Give the smallest angle for the same value of n. To determine the number of the crossing n on site, the point where 1 meter offset gauge face of the turnout track is marked. The distance of the point in meters from the theoretical nodes of crossing gives n. In this method, the alpha refers to the angle of the crossing. Then, cotangent alpha equals n over 1, which actually means the value of cotangent alpha represents n, the number of the turnout. Lastly, let's take a look at the isostasis triangle method. Like centerline method and right angle method, in this method, the alpha still denotes the angle of the crossing, but n here is taken as one of the equal sides of the isostasis triangle. So we have the sine of alpha over 2 is equal to 1/2 over n, which simplifies to 1 over 2n. It can also be transformed into the cosecant of alpha over 2 equals 2 times n. So n equals 1/2 times the cosecant of alpha over 2. So why calculate n? Well, there are relationships between the number n, angle of turnout common crossing, and the turnout branch radius. In other words, the number typically indicates the radius of the curved portion of the switch. In the field of track engineering, it's a well-established fact that as the angle of the crossing increases, the number of the turnout n required decreases. Consequently, as n decreases, the train's speed over the diverging track is reduced. Meanwhile, the length of the turnout will be shorter because of the short radius detected by increased crossing angle. The converse is also true. It's important to note that using formula is rough approximation, and the different railways may use slightly different formulas or criteria for assigning switch numbers. Additionally, other factors such as the length of the switch and the angle of the curve may be also considered when designing and identifying railway switches. For tramways, the principle of the switch is the same as a railway track. However, the following structural difference should be noted. The curving switches and trams and metros can be much lower by the lower speed and bogie distance, so the switch length is shorter. The switch can be integrated in the pavement of the road. The rail type can be different by the lower load and speed. Sometimes switches from the trams have no power and have simple engines. The blades will be moved by the tram wheels. The switches are operated from the train driver by signal, not from the operation center. By tramways, there are much more crossing at more different angles. In China's national railway system, the common railway turnout numbers indicated by the number of common crossing include 9, 12, 18, 30, and so on. Turnouts with a number of 9 or less than 9 are primarily used within industrial and minor railway networks or humping marshalling yards. The other numbers are suitable for maintaining railways and station tracks, with 9 and 12 being the most commonly used. Larger numbers turnouts like the 18 and 30 are typically laid in sidings, usually found in high-speed railway tracks. In China's urban rail transit systems, turnouts numbered 7, 9, and 12 are frequently utilized, with 9 and 12 being used on the main lines and 7 or 9 in the depot areas. In this lesson, we have explored the various methods for calculating the number of turnouts, a crucial aspect of railway track design. Understanding the relationship between the turnout numbers, branch radii, turnout length, and the permissible speed through branch tracks is fundamental for ensuring safe and efficient train operations. This knowledge empowers railway engineers and operators to make informed decisions when planning and constructing rail networks, allowing for the smooth flow of trains through various branch lines and sidings. The intricacies of the turnout design and associated factors are key elements in the art and science of railway infrastructure, contributing to the reliability and effectiveness of rail transportation systems. Okay, this is all of today's lesson. See you next time.